And now we'll be introducing the first speaker, Logan Thomas. Went to Oklahoma State University in Wichita, where he received a Bachelor's of Science and I think Master's degrees in aerospace engineering. He has a decade's experience in aerospace, specializing in structural optimization and FEA. At JetZero, he serves as a structural analysis engineer, leveraging prior experience to lead the production of the wing stress team. So thank you, Logan.
Okay. Okay. Yeah, so my name's Logan Thomas, and I'll be giving y'all a introduction into how we used HyperXpert's in some of the trade studies that we're doing for our blended wing body aircraft at JetZero. So I want to first give you a brief overview of the trade study that I'll be giving you a use case for today. That use case was that we were wanting to determine a weight-efficient wing to center body load path that satisfied both producibility and manufacturing requirements. So this was a large it was a vehicle level trade study, really. It involved both the wing and the center body structure. And so HyperX was the tool that was necessary to solve this solution. We were looking at two different load paths here, load path 1 and load path 2. Not going to go into specifics on that, what those were, but it involved the wing to center body transition and the load path through the center body. The trade study scope, just to give you all a taste of the size of this project, it involved this portion of the vehicle. It was a portion of the left-hand side center body with the wing section, and included the leading edge and trailing edge structure. It had symmetric boundary conditions at BL0. The model statistics, it had over 95,000 elements and over 80,000 nodes for both of the finite element models. There were two different finite element models that I was working with, one for load path 1 and one for load path 2. The loads that were applied, I applied both flight and cabin pressure loads, resulting in a total number of design load cases of about 2,000, roughly. And so I want to give you a trade study sizing workflow. This is a workflow that we used, that I used for this trade study. However, it could be adopted to any number of trade studies. It works well with very early concept development phase. So the initial phase is to obviously create your FIM. Do all your pre-processing in the FIM, do all your VMT checks, get your internal loads. We feed that FIM into HyperX and do a anchor point sizing loop. So in that loop, the main point there, all of the workflow is pretty typical of your HyperX workflow. You're assigning load and analysis properties. The main difference is that we create a unique anchor point design property. And that's going to be useful for when we run the results through HyperXpert in the next step. And I'll touch on that later in the presentation. Next step, after running through the sizing using the anchor point design properties, we run that through producibility sizing. And this is where we take advantage of HyperXpert, and we're taking advantage of HyperXpert using those anchor point design properties and the redistributed internal loads from the anchor point design results. Then we review the results in HyperXpert, down select to a more producible design property that will then feed in back through HyperFEA and get some new sizing results. And there's a further step past this, and I'll touch on that later in the presentation. But as far as the presentation, I'm mainly going to be focusing on these two steps here. Just want to touch on the type of analysis technique that we're using. I think this is one of the tutorial wings built into HyperX. And we're taking advantage of the smeared mesh approach, mainly so that we can vary the stiffener spacing within the wing structure. And just touching on the types of failure modes that we're investigating, these are all of your typical failure modes that you would want to check in your analysis. Laminate strength, panel buckling, local buckling, crippling, that sort of deal. And so getting into anchor point sizing, I think Craig touched on it yesterday during his tutorial on HyperXpert. Anchor point sizing, the anchor point is the unique design, or it's a unique optimum design for every zone within your structure. So it's the lightest weight, as all of the zones have positive margins of safety, but it's also the least producible. You can have your variables in each of your zones can vary wildly, leading to a non-producible design. And so that anchor point design property, what would that maybe look like, and when should you use it? It's really useful to use this workflow during the preliminary design phase when you're trading numerous variables. You don't know what the stiffener spacing is. You don't know what your stiffener looks like, and so that's the primary point of when you should use anchor point design properties and use this workflow. What does the anchor point design properties have? It's probably going to have coarse step sizes. It might use effective laminates if you're wanting to look at different stiffnesses without taking advantage of laminate families. You could also include laminate families, as Greg was shown yesterday, if that's the way that you want to go. And then from that, you're probably going to have a large number of candidate designs. So I don't know if you can see the bottom picture there, but that's close to 73,000 candidate designs for that design property. And so you're probably going to be trading runtime versus number of design variables. But that might not be an issue anymore with the solver. So, something to look forward to there. And why are we doing this? So by running a sizing loop using the anchor point design properties, you're going to get a new FEA starting point with updated stiffnesses and updated internal loads that you can use for the producibility sizing within HyperXpert, step 3. And so for the producibility sizing, again, looking at this portion of the wing, we are going to focus on the wing skins. So we split the wing skins into 3 different zones for producibility. And this isn't zones in the HyperX sense, this is really sets. So zone A was a forward set, zone B was a mid set, zone C was an aft set. And for those different sets or zones, we had some producibility assumptions. We wanted stringer stiffened wing skins, for example. You could also trade different type of stiffening concepts, right? You could trade sandwich, for example, using the same workflow. But this is just an example here for you. All of the zones within should have the same stringer tooling mandrel shape. So the H stiffener should be constant. And all of the zones, but all of the zones might have different stiffener spacings. So the spacings might not be constant based on the location where the stringers drop off and whatnot. You might allow different stiffeners in the forward, different spacing of stiffeners in the zone A compared to zone B. So now going into the producibility sizing and what HyperXpert is. It runs a full factorial design of experience solution based on your input design property values. And you can see the run set that I have there. It has a bunch of different design properties, a bunch of different analysis properties, a large number of zones, a large number of sets. you only have to run this once if you set it up right using the anchor point design properties. And so why should you use this? So using this workflow, you can determine the most weight efficient and more producible combination of design variables across a number of sets or structures. When should you use it? Find the optimum design variables that that yield a producibility design, and those variables are unknown, right? And how should you use it? I touched on that already. Using the anchor point design properties and running that through a sizing loop to get updated stiffnesses is critical because your loads might not be correct if your stiffener geometry is different than what you're assuming or than what you're running through HyperXpert, right? And so from this, we can see for all of the structure that I was analyzing, we had over 2,000 possible design solutions. All of those are positive margins of safety for the structure. Going into HyperXpert now, looking at a Pareto frontier plot for the wing skin sets. So I have zone A, B, and C in blue, red, and green, right? And on the right-hand side, those three dots are your anchor point sizing results. Those should match what you get out of step 2, your anchor point sizing loop. And those are the least producible, right? They have a large number of variables that are unlinked. None of the variables are unlinked, in fact. And as you move to the left on the chart there, they become more producible. More of the zones become linked together. The stiffener spacing is linked across to all the zones. And you get a more producible design, but you're increasing in weight, right? And so in this case, there were 218 possible design solutions for the wing skin itself. All of those have positive margins of safety. And so then the next few slides, I kind of want to show you all how I down selected and how I interrogated the results within HyperXpert to be able to choose the optimum design. This first step, I actually changed the x-axis to spacing. So we went from a lower spacing to a higher spacing, and we had 4 different spacing options. This is where, when you're setting up your anchor point design properties, the number of steps, that's going to be the number of points that you have on this chart here. So it's very useful to have I would say at least 3, some would say probably 4 or 5 steps, so that you can get a nice curve and find the local or global minimum in that curve. And so I start off by looking at the spacing, pretty flat, honestly. But again, that's all looking at different stiffener heights as well, and stiffener widths. So what I did was I constrained it. I said, okay, I only want to look at spacing C, throw out all of the other spacings for right now. And when I look at spacing C, and then I change the x-axis to stiffener height, something interesting happens. I see that for zone A and B, the lowest stiffener height option is now no longer available, right? Your stiffeners get wider or farther apart, resulting in or needing more inertia capability to show positive margins. So the lowest stiffener height is no longer an option for zones A and B, meaning that you can only choose the height B and C in this case. So what I did after that, I constrained it to height B, same thing. And then I changed it to looking at the stiffener width, all right? And it's still relatively flat. You can see a slight downward trend as we increase stiffener width, right? And so after getting to this step, you can then extract all the results, right? You can pick on all the points. It'll bring a table down in HyperXpert, and you can actually throw that data into Excel and create a pivot chart. And so from this, this is showing different spacings by set, the weight by set for different spacing options, as well as a function of the stiffener height and stiffener width, right? Lots of data to look at here. And by separating them out, like I said before, you could have different stiffener spacings in the different zones. And so that was really what I was looking at here is, would it be useful to have different stiffener spacings in some of the different zones? One other thing to point out, the dashes are actually the anchor points. So that's what I'm comparing against to see how much weight am I going to increase by making a more reducible design. And then I can come over here and I can actually group that all together, all the zones together to look at the overall weight of the wing skin, right? And so you're looking at the combination, the different variables, your stiffener height, your stiffener width, your spacing, seeing how that all plays together. And the bar on the far left there is your anchor point. And so what we can see here is that by going through HyperXpert, you can find the most producible and lowest weight design variables to use for your producibility sizing. And this is probably, at this point, you would go and you would take those producible design variables and go and rerun the results in HyperX and get new sizing. And so there's a 5.5% weight delta there. This can vary quite a bit based on the structure that you're looking at. You can also do this okay. Sorry, I'm getting like a reboot on my screen. Okay, I got it. Yeah. So why did I extract all this data, right? I only ran HyperX one time, one sizing loop, really, to get all this data from HyperXpert. And where it's useful, why I extracted all this data, say my manager comes to me and says, hey, that stiffener height doesn't work. What is a different, what can we do next? And I can go and look at this chart very quickly without having to rerun HyperX. Now you will want to do that, right? And say, okay, well the next option would be X, right? Looking at the chart, you find the next producible option, go with that. You already have the data backed up. And like I mentioned, you can do this for spars, you can do this for ribs, any other structure really on your aircraft. And that's what I did actually. This is just a case study on just the wing skin. And what did I do next with that, right? I have a lot of data. I'm comparing two different load path options. Well, I utilized the HyperX dashboard. I don't think anyone's really touched on that this week. But the HyperX dashboard was utilized a lot to store all the data and create comparison charts. So you can upload the data to the dashboard, and it looks something like that. And then once the data is in the dashboard, it looks something like this. You have upload sets. That's basically a screenshot of all of your data in the database that you can interrogate and create charts from. And so that's what we did. We can quickly create graphs using the HyperX sizing results. And so this is a chart showing total weight versus display set. So on the far left is the full trade study structure, the full FEM structure, the weight of that. And then I have it broken out into the wing and the center body. And the different bars represent the different sizing steps, as well as the load path options. And one thing that I didn't touch on previously, so step 3 was to do producibility sizing, and the approach that we took was to run that with effective laminates. We took that a step further and actually generated laminate families. And the next step, and that's what LP stands for. And you can just see the trend going from a more least producible design to a more producible design. Another thing that happened was my manager came to me after I ran all this stuff. I was like, hey, I've got a different material system that I want you to analyze. So I just added that to our database and reran HyperX using the most producible design and then we were able to compare the results there. Another really cool thing that I like to do within the dashboard is create these percent controlling criterion plots. In this case, I'm comparing the 2 different material systems. So looking at the different zones, what is the percent of that zone by weight that is controlling? And so you can see here that the material system 2 was slightly more stiffer. And so that changed the controlling criterion, right? You can see zone C, that green bar increased quite a bit. So some key takeaways. Again, the objective, find a weight efficient wing to center body load path that satisfies producibility and manufacturing requirements. We were able to do that with HyperXpert by trading many different variables in HyperXpert without needing to make additional reruns. Those 2 major load path configurations, they were analyzed in a limited time frame. I was the only one running this project for my team, and I did it in less than 2 months. And that's like creating the FEM for both load path configurations, going through all those sizing steps that I showed previously. This allowed us to down select a major structural load path that will be used in future production activities. So with that, that's my conclusion. Any questions?
So this is probably maybe a question for the HyperX team as well, but how would you handle a situation, for example, some of your stiffeners, suppose they're hats, we have manufacturing constraints at Bell where the radii, the features of those hat stiffeners are connected to the ply count, right? So we can't go above a certain ply count with a certain radius, and therefore we'd have to increase the radius. So I know that you had a restriction for keeping a consistent tooling mandrel surface. But say you had an additional constraint where you couldn't add a certain number of plies until having to change that geometry of that tooling surface. Then of course you don't want to go to overly generous radii because that's just trapping weight potentially. So just kind of curious how you could handle such a constraint in a similar study.
Yeah, that's a good question. By radii, are you talking about the radius of the stringer in the hat stringer?
Right, yeah.
The
Either the crown radius or the
web
foot radius here.
Okay.
Yeah.
Yeah, that's an interesting question. I think I'll have to get with you after that, or maybe the HyperX team can talk about that.
That is a good question, and it is, later today at the end of the conference, we would want to hear these kind of requests. We don't have that capability, to be honest. And that's okay, you know, to lay it out on the table, what we do and don't do. We don't consider the radii in the sizing process. Because historically, I guess, from a failure analysis perspective, normally, I don't know, maybe you guys do, but we don't see stress engineers really looking at that, maybe for flatwise tension issues or something of that nature. But we would be willing to consider adding these kinds of features into the software to handle this. As you know, we are making claims of pursuing manufacturability, right? So you're pointing out to us a need that we would need to consider, you know, to get that manufacturing capability that we want. So, yeah, let's have a follow-up conversation about that. It seems like it would be feasible, quite feasible for us to do it. No one's ever asked us before to do this, so thank you.
There is a way to set up your design properties such that you can pair laminates with geometry that's suitable for the laminate used on the cross section. You know, as Craig mentioned, the radius is not an explicit parameter, but if it affects like the width of the crown or the height or the overturning the angle of the upstanding web, you just pair the geometry that's appropriate with the laminates into a specific design, and then you have another mandrel design with that geometry, and then another mandrel geometry in another design, and you can just have it cycle through those, basically.
Right.
That's how we'd handle that.
Yeah, because the flange radii would just be a function of the rest of the geometry. Right?
Exactly.
So, okay.
Yeah.
On the last slide that you had for the controlling criterion, is there a way to dig into how much of an impact something has changed to see if something was very like close to strength and stability versus now maybe you're fully stability driven? Can you dig into like two specific producibility cases to compare those things?
Yeah, you're talking about the percent strength driven, percent stability driven?
Yeah, like for a particular zone that now was previously strength driven and is now stability driven, is there a way to assess whether you're now going too far one way or the other to not have really a balanced design?
Right. I guess one thing that it doesn't show here is like your critical margins. I'm not quite sure if you're able to do that for like the zones, I guess. But from this, you can see the percent of that zone by weights, so it's a weighted average essentially, that is driven by stability or is driven by strength. If it's driven, I don't know what color that is. the other green for zone C on the left plot, that's controlling a large portion of zone C, right? I can't tell you which controlling criterion that was, but maybe that was stability driven. Well, I increased the stiffness and now it's less stability driven. It's more strength driven. Now it's more 50, it's closer to 50-50, right? So we're getting, lighter weights and in that zone. Yeah.
Thanks.
Thanks, Logan, for the presentation. It's good to see a real-life HyperXpert example. My question may also be a little bit more for the HyperXpert team, but when you added that other material, was there a way to effectively append those cases to the HyperXpert model so that you didn't need to rerun the entire... Effectively, you could add the material as another variable to the previous HyperXpert study and just effectively append another variable and data set to that original matrix? Or did you have to do it in a separate HyperXpert because you couldn't append?
Yeah, so what I ended up doing, I took the final producibility design property, and I just subbed that material system for a different one. But you could quite easily go into that original anchor point design property, replace that material system in there, and then go through the same sizing step with that material system. Maybe you'll get different results. It's entirely possible. I didn't go through that entire process for the sake of time because my manager was wanting that answer very quickly. But that's definitely something that you could do. Yeah.
I guess the last follow-on to that is, does HyperXpert require rectangular matrix input? If, for example, if you were to do this again, knowing that height A might work for spacing A, but not spacings B, C, and D, do you have to run all of those again just because to make the data rectangular, or can you specify, I want height A and B and C for spacing C and D, but only height B and C for spacings A and B?
I think Craig's shaking his head. Yeah. I mean, I guess Craig's shaking his head, but yeah, I think so. It'll run the DOE, but there's also I'm not exactly sure what it does. Maybe the HyperX team can say something to it, but you can limit the design space.
The question I understand is that you don't want to have to populate off diagonal terms essentially when you say rectangular, right? So yeah, you can create your design properties such that you kind of decide what chunks of area you want to do the optimization in. Yeah, so.
Thank you.
I think you had one more.
With the HyperX dashboard, I'm very unfamiliar with it, but is that something that anyone on your team is able to pull up real quick and doesn't need any license or anything like that to view the HyperX results?
Yeah, that's the nice thing is, you could add a designer even to the dashboard or your manager, and they can go and you can share the graphs with them through the dashboard, and they can pull up those graphs and see the results right there. And the results get updated. As soon as you upload a new set and add it to that graph, it's automatically updated. So makes creating presentations for managers and whatnot very easy, because I don't have to go and find the data in HyperX, copy it over to Excel, and do all that. So.